Okay, we're in the middle of lecture 29, which involves this guy that Bentley has just asked about. He asked, what is the lens vector? And I guess the flippant answer would be, it's pure magic. But it has some very simple explanation. I would say this is the simplest I can come up with that shows that it is a conserved vector that gives you the equation of whichever conic section is involved. It could be an ellipse, and that would imply an attractive Coulomb field, or it could be a hyperbola with positive energy. This is negative here for bound state. Positive energy, attractive, a hyperbola that orbits around an attractive point. Or the third case, it could describe a hyperbola in a repulsive potential, something that's avoiding this focal point, and of course there's nothing there. There's, say, a positive charge there in a Rutherford scattering example that we did first, without the use of all of this. So the real idea is that this epsilon is analogous for the Coulomb to the Stokes spin vector for the harmonic oscillator in 2 dimensions. So it's a very convenient descriptor of the state, classical state, you might say, of the, in this case, 2-dimensional oscillator, in this case, a 2-dimensional orbit on the plane of a 3-dimensional Coulomb potential field. So we're going to use it today, show you how some more things about it, in particular, toward the end today, when I show you the graphical development of orbits, and particularly the launch optimization, things that you can do with this vector that really be hard any other way that I know of. And the usual technique of just solving differential equations and putting initial conditions in is really clumsy when you want to ask questions about what's the way that I can shoot this thing and have it go to here and have such and such a speed there, or something like that, you'll see. Also, it's very powerful when it comes time to do the favorite kind of problems for this class, and that are envelope problems, where you have a whole number of trajectories going out and making some kind of shape. Like the Rutherford scattering, that's a very simple one, really, compared to some of the others we've treated. So we're going to be returning to the volcanoes of Io, except now we're going to be doing them exactly for a Coulomb field, not for constant gravity. And that's another thing that this thing really helps you understand. So basically, the epsilon vector is a vector that points on the symmetry axis between the foci, or along the line that carries the foci, has a length equal to the eccentricity of the orbit, and like angular momentum, r cross p, it is conserved during the orbit. That's the thing that's holding the frame of the orbit, you might say. So these two objects here, these two 3-dimensional vectors, but once you've decided on an orbit plane, the magnitude of these vectors are the things that you write the equation with. For example, L squared over Km is our lattice radius, and the lattice radius is the height above the x-axis at the focal point, the radius of the focal plane, if you were to imagine a plane right there, and this was a 3-dimensional ellipsoid. Okay, I can't think of anything more at this moment to say, except that when we do the dot product of epsilon with r, we get the equation of motion. When we do the epsilon product with p, which we spent some time on in the last lecture, we always get the radial component of the momentum. That is, the momentum dot the unit radius vector. So the radius vector is the thing that's being described by this equation, and that's the magnitude of the radius. The angular momentum is sitting perpendicular to this plane here, the L vector, and P, we discussed that a little bit, P follows a circle, and its orbit is very simple, and we ended the class last time with that. So before we go on, let me make sure that description is okay. Does that make sense? Yes, you know a little bit more about what the epsilon vector is. It's, you know, it's really something that should be every mechanics text, and it's also should be in the quantum mechanics text, because it's a really elegant way to do the Coulomb field quantum mechanically. And I don't think everything about that has been explored yet. I think there's a lot to be done with the vector that they call A. Very often you'll find it listed as A, and it's Km times epsilon that they're talking about. But I think for us, the epsilon is the thing that we want. So this the commutation relations for this takes a little bit of algebra to derive that. I'm looking for better ways to do that. But those commutation relations are the same as, or they are similar to the commutation relations for this. And in fact, commutations of A with themselves gives L, and commutations of A with L gives A. So there's an algebra of the orthogonal group in 4 dimensions that's being described by that system of operators. Okay, now what we did last time was look fairly closely at that epsilon ratio for the velocity or momentum. We took m equal to 1, so velocity and momentum are the same thing here. And we noticed it for hyperbolas as well. We noticed some things about the things that we did before this, major axis, focal axis, all that sort of stuff. The physical constants of motion, energy, and angular momentum being related either to the Cartesian parameters of A and B, or to the, shall we say, polar coordinate parameters of epsilon, eccentricity, the factor that makes the focal distance when multiplying the semi-major radius. The lambda here, which is a Greek L to go with the L that's used for angular momentum, is the radius at the focal plane. And there's nice relationships that relate them all, and the only really complicated one is the energy, the angular momentum. Fairly simple, and the energy in terms of epsilon, but the energy in terms of the major radius, the semi-major axial distance, is just k over 2e, and we've used that for our Rutherford scattering. We're going to use it some more for the more generalized orbits, because you see the 2a that's in the denominator of the expression for the energy, with the numerator being the Coulomb constant, whether it's gravity or electrostatic. The 2a is the length of the string that's making this orbit. When you put a thumbtack here and a thumbtack here and a string up to the orbit and make the string exactly 2a in length, that will then draw the ellipse. And there's a similar construction for the hyperbolas where instead of having this sum of these two radii be equal to 2a, the hyperbolas all have the difference between the radii be equal to 2a. That's a big difference that's causing us to have different formulas for some of the quantities here. As epsilon gets bigger than 1, we're in the hyperbola territory. Here epsilon is only 3/4, so you have a pretty nice little egg there, an elliptical curve for that. So this is stuff we did last time, and we're going to do it again, but using the epsilon vector more carefully. Now, we already talked about the momentum geometry and the equations associated with that. This is just an algebraic development that's fairly sweet. It gives us equations for phi dot and r phi dot, and r squared phi dot. Those are all of interest for various things that we do. The Cartesian x and y dot are the ones that we plotted out. I remind you that they, except for one extra little epsilon there, which would be gone if epsilon was 0, that's a circular orbit, they obey the sine and cosine components, respectively, with the thing. Now, remember, we have the x-axis this way along the eccentricity vector, y-axis is perpendicular. The y-axis for the momentum has the cosine, and the x-axis for this thing, momentum, has the sign with a minus sign right there. So that's what gives us this circle here. That's the plot of where the momentum vector is going to be coming out, drawing it out of this focal distance right here. So as we went through this thing, we saw the various momentum vectors depending on where the radius vector was. If the radius vector was there, this is the thing that gives that. And then if the radius is here, then you use that to locate a point here. That's giving this vector right there, and so forth. There's one more here right at the lattice radius. And finally, there's a really fast vector that corresponds to making the perigee turn. Okay, now this epsilon vector business, this is where it does the whole job. We can go out in space anywhere, set down a Coulomb center, and then anywhere we want, put an initial position, and then decide to shoot that thing with some velocity or just drop it. That's called a diving orbital, which is in atomic physics called an s orbital. It's something that has no angular momentum. It just falls in and bounces back. But that's not a very small set of orbits. Most of them have some velocity in some direction. So you name a velocity, initial momentum or initial velocity, and this construction that we're putting together using the epsilon vector's geometry is rather nice, rather simple. I'm going to show you some of its power today. That would be most of the lecture, in fact. Okay, now this is just to remind you what we did last time. Is, as I said, pick a launch point, pick a initial momentum direction. We don't have to specify its length yet, but we will do that, and it comes in the form of a ratio of your kinetic energy to your potential energy. At this point, neither of those are constants of the motion, but at this particular point, they're the ones that are going to characterize the orbit initial conditions. And let us draw the whole orbit. So that's kind of a neat thing about this. So basically what we're doing here is we're copying this, call it the elevation angle, radial elevation angle. Start with something that was a diving orbital and raise it up some amount gamma, okay? And that will correspond to the a complement of that. If this is say 20 degrees, this is 70 degrees. That's the alpha that we'll talk about later. We use that when you're sitting on a surface of the Earth and shooting a cannon. You have an angle alpha, which is the complement of this. This is the elevation relative to the horizon, the elevation relative to the radius. They each have to sum up to 90 degrees. So when you have zero elevation here, I'm going to have, that's horizontal elevation relative to a horizon that's right here. I'm going to have 90 degrees for gamma, the elevation relative to the zenith, or I should say the nadir, the radius to the center of the Earth. Okay, now the idea is to copy that elevation, in other words, make twice that. You're going to see this factor of 2 and 1/2 playing a role for this. And eventually what I'm going to show you is a nice piece of graph paper with a protractor conveniently stuck to another one so that you could just go in there and without having much more than a ruler do coordinate calculations. But here after doing this copying, right here we have a double angle, and you extend that line, and that is the locus of the focal points, the focus locus. Somewhere on that line is the prime focus, F prime. F is the center, but out in the middle of the vacuum somewhere is a magic point that is the other focus for a conic section of some kind. The beauty of this epsilon vector is it knows them all. Okay, now the idea of this construction is to make this energy scale, and that's a fairly easy thing to do. On the piece of graph paper that I'm going to give you, it's always perpendicular to the momentum vector, and as we're going to see, it's basically taking care of, and I'm going to go ahead on this computer here and get to the point where the vectors are being shown so we can talk about the pieces of them. But basically this line here is represented by this thing, P cross L. We'll see that in a minute, but that's where it comes. That's how we're putting this together. So the idea is then that if a beam of light were to emanate from the force center, the unprimed focus, and reflect off of the momentum direction, the momentum plane here, it would go down this line, or if it were going to reflect the other way, it could go up this line. But in any case, it's going to somewhere hit another focus. So that is the idea behind that extra, that's the idea of why the focus has to be somewhere. And then this ratio scale here, the one that's going to have a scale that gives us the initial KE over the initial PE, that's bisecting that angle of incidence, angle of reflection equality, giving us again a complement to the gamma angle right there. So keep that in mind as we build these constructions. Sometimes we don't say that over and over again, but that's a good thing. Anyway, once you have this thing and you mark it off, using the circle on which you're launching, the planet, if you will, the Earth, using that as a scale, starting with 0 here and working your way into the negative -1, and then further -2 minus infinity. So this ratio can be arbitrarily large, but if it's an attractive potential, it's going to be minus. This is positive definite, e squared, but this thing in the denominator is minus, so that is as far as you want to go. Obviously, when we reach this point, we're at escape velocity. This is a ratio of initial velocity to escape velocity squared. That's what this R is. That's probably more familiar to you. Okay? So far, so good. Is this making sense? Even though you don't have yet a proof that that equation gives this. I'm going in this backwards, so to speak. Obviously, I had to screw around a lot to get this construction, so just saying, well, here it is, and then we'll make sense of it afterwards. Okay, not much else to say about that, except that as soon as you want to pick your initial speed, now I do want to specify the length of this vector here. And of course, anything I do this way is perfectly good going that way. You're going to have an orbit that closes on this if it's a bound orbit. So you can play the clock backwards and have momentum go this way. It's going to change very much. It would just give you a different part of the trajectory first. But in the case of the ellipse that's going to come here, and here I've picked a ratio of -3 to 8. That is, the initial kinetic energy was 3, while the initial potential energy was 8. Ratio of 3 to 8. Okay, but with a minus sign, this is attractive. Okay? And once I've picked that 3 8s, there's 2 8s, 3 8s would be about there. That right there is your eccentricity vector, and the eccentricity vector points at the next focal point. So that's what's going on right here. I've picked -3 8 for the energy to give a particular magnitude of my initial velocity, and that is indicating where the other focus is. And once I have that, I'm ready to, if I put 2 thumbtacks in there and a string here, I can draw my ellipse very quickly, and that's what I used to do on the blackboard. The problem is, and it also can be done on a whiteboard, but the problem is on whiteboard, suction cups slip. We haven't worked that out yet. On the blackboard, it's got little pores in it, so you have to work real fast or the suction cups pop out. You know, these are little problems in working with stuff that's 3,000 years old, right? Or more or less. For this first run through with a video, I'm not going to do this construction the way we used to. We'll just let the computers show us the results, and I'll give you some graph paper to make your own very easily. Anyway, this is construction of the orbital trajectory once you have these 2 foci in the initial point. Here we're talking about -3 8 ellipse, and the analytical geometry is coming. Okay. First, look at what happens if instead I decided I wanted to point out something that had a both -k, that means a repulsive Coulomb potential, and if it's a repulsive Coulomb potential, then what you're talking about, remember how we had that minus, this is a minus, so you have a positive repulsive Coulomb potential going here, and that means your energy is always greater than 0. There's no choice on the matter. So that's what I'm going to get if I point my epsilon vector up like that, if I take my thing into the positive region. And between here and here are all of the points associated with repulsive orbits. There's not very much there. Now the other side of the coin, this is for r equal plus a half hyperbola. The other side, you see this is a ratio that's positive. The other side of this line here goes negative, negative, negative affinity, and as you point more and more this way, finally you turn around and you start using the region of the focus locus that lies above this point. So all the foci for the repulsive orbit are in here, and the attractive negative ones are from here to -1, and then all of this and all of this are covered by attractive hyperbolic orbits. So they're the ones that dominate. And that's appropriate for the universe. Most of the stuff that's out there isn't orbiting around anything. It's just flying around like Halley's Comet, and every once in a while stopping by to say hello, and then it's gone for 70 years, right? So most of the things that are in the universe are going to be taking up positions from here to infinity and from here to minus infinity. So that's what we're going to see some examples of that. But in any case, this particular one gives a hyperbola that's repelled by this. All of the other points here would give hyperbolas outside here. All ones would give a hyperbola that was like this ellipse that we just looked at, okay? Except we would throw the thing so darn far, you see, that it would be maybe a parabola and then a hyperbola. So we would be making a hyperbola that was attracted to that point. That would be curving into it instead of away from it. Okay, so this is a very different way of looking at these things. I would say it's the only way to look at it, because just with a bunch of formulas, it's really hard to look at it. You have to plot the stuff out and actually see what it is. Okay, now let's look at the derivation of this geometric construction based on this equation. We're basically, the job here is to make the epsilon vector for three different cases. Focus locus for k greater than 0, that's attractive, and e less than 0, and then as we go epsilon or energy greater than 0, we talk about the stuff that's below there, okay? Let's just look at what we did. First of all, we define an initial point, which is right here. We define a direction, okay? That means we set the gamma angle, okay? We copy the gamma angle out to get the focus locus, okay? So that far is clear, except that what we have to see is how this equation can be taken, say, deconstructed. So what I'm doing here is I'm taking P cross L. Well, that's P, magnitude of P, which is MV0, magnitude of L, okay, remember it's pointing out on the screen, which is MV0 times the radius, initial radius, R0, times, and it's cross product, sine of gamma. That's why I use gamma right here. It's the cross products sinusoidal. Okay? Now, it's all divided by Km. All right? So, what we have here is a unit vector pointing in the direction of R, and to that we're subtracting this vector LP cross. Okay? That's the vector P cross L, this thing right here. Okay, now just shorthanded by calling it LP cross. Okay? LP cross is this way. Okay? If P is positive, if it's negative, it goes the other way. See? So that's the point. It can either be in the negative region or the positive region. Right now I'm looking at that rare case of a repulsive orbit. Everything's positive physically. Okay? So, there is epsilon being a sum of something that has a sign in it, the sign gamma here, okay? And here multiplied by 2r. It's the same thing as this down here, okay? And that was one of our construction steps, was to copy this arc over here. That's the way we used to do it. In graph paper, we don't need that anymore, but still it does. And this is the thing written out in the way the equation would have us given. That is 2 sine gamma times mv0 squared over 2, and I'm going to multiply by 2, okay, so I get kinetic energy here, and then I've got an r right here, which I'm going to put in the denominator of the denominator, okay, and that's your Coulomb potential right there. So there's your Ke, there's your Coulomb, that's where the ratio comes from. And that's basically it. That's the construction that this is showing. Okay, it's not that difficult once you get it, but it took me a long time to find it. Okay, I'm hunting around for, in fact, I didn't know this was possible. I should have known, because the Coulomb field has an O4 symmetry, therefore geometry exists. Now we know that. There's a group behind it. Group's just grown up geometry. There's going to be geometry. Okay? So, here's writing a thing as a vector. Cosine gamma, sine gamma, plus 2 sine gamma. And this thing only is that second component. Okay? This thing right here has possibly both. Okay? And so that sums up to that. That's your epsilon vector just written out in components. Okay? For gamma equal 45, which is about what that is, and r equal to about a half, which is what that is, we would be getting 1 over the square root of 2 and 2 over the square root of 2 for the epsilon vector in this coordinate system, which consists of that and that. Okay? All right? Pretty good. Now remember, the eccentricity parameter is defined by cosine squared, and this is what's nice, is that it's this 2 times this ratio plus 1 squared times sine squared. That's kind of a neat thing. We're going to talk some more about that, but that's really what we're seeing, just from the algebra and the geometry here. So this is the usual expression for eccentricity parameter, and you'll notice it's going to be plus or minus, depending on whether we're talking about ellipses or hyperbolas. And you see, ellipses really have a pretty small role here. That's their area for having focal points. Okay, let's see if there's anything else I need to say here. I think that's enough. We'll come back later on and deal with it. I'm going to go ahead on this screen right here and put this one up here so we can refer back to it. There's our ordinary way of doing conic geometry. There's our way of getting the momentum and velocity into the order of the circle. And then, by the way, that's the thing you can do very easily as you're building the construction of the positions using this. You can get the momentum as you go. So that's too far. I think I'll stop right there. Okay, those should be identical. Okay. Now, just a little bit about this algebra. R is PE-KE ratio, and it's also B squared over A squared. So the epsilon, this is the equation we're talking about here, 1 plus 4, that energy ratio times the energy ratio plus 1 sine squared. So that's you see, we have now, in addition to A and B, that's Cartesian, and then epsilon and lambda, that's eccentricity and lattice radius. That's sort of the polar parameters. Now we've got one that sort of rules both of those, and that's these two guys here, the gamma angle, okay, and the ratio, R, okay? So that's totally new. I've seen no one else has ever tried that. But you see, there's no Swiss Army knife that's good for every one of these things. They're complementary, these three sets of things. Sometimes this one is really powerful and these stink, you see. Cartesian, Cartesian doesn't show you much about the curvilinear behavior, okay? The epsilon Lambert, pretty nice. It is a polar problem. They probably win a lot. But I would hold these guys, as you'll see. I'd hold this R, the ratio, and the gamma very highly, because it's not tripping over the difference between a hyperbola and an ellipse. It's going smoothly between these regimes. It's sort of analytically continuing very nicely. Now you'll notice that right here I have to say, for an ellipse, your eccentricity is going to be having a minus sign or a plus sign, because epsilon has to be less than 1 for the ellipse and greater than 1 for the hyperbola, and equal to 1 for the parabola. Don't forget the set of measure 0 that is hiding between those boundaries. Now, writing this out, that is fine. So this is an equation that you can just write this thing right here as your minus b squared over a squared or plus b squared over, depending on what your R value. R value is going to tell you whether you're hyperbola or an ellipse, so that's fine. So what you're implying, you see, when you see this, is that R times R plus 1 is less than 0 here and it's greater than 0 there. Okay? Or another way to say it is R squared is less than R here and R squared is greater than R for these guys, the hyperbolas. Okay? Or you could say R is less than 1 for the ellipse and greater than 1 for the hyperbolas. Both kinds of hyperbolas, the ones that live over here and the ones that live up there. Okay? So that, I think, is important. And that's where I'm getting this idea of the little region here for the repulsive orbits, of which there are no possibility for E to be less than 0, is, very small. Okay? So it's less than 1 and not negative. Here's where less than 1, the magnitude is less than 1, but it is negative. And that's the region of the bound states. The ellipses live down there. Okay, let's see if there's anything else I can say here. Okay, now remember this one. Minus K over 2A, that's total energy. KE plus PE. That's the sum. And then there's the ratio, KE to PE. Okay. And of course there's the difference between KE and PE, which plays a role in the, see that E minus V there? That plays a role as coefficient, the parameter of the oscillation parameter of the Schrodinger equation. Right? Okay, so we're kind of playing with all of this stuff in a nice way here. Okay, so I'm writing this KE plus PE, and the KE is R times PE, so that's where I get an R plus 1 times PE. There's the PE. 1 over 2K is given by R plus 1 times 1 over R. Okay, and we're going to set R equal to 1. In our geometry, that's what we're going to do. We're going to use that as our length scale. Whatever you gave me as my initial radius, I'm going to use that forever as a length scale throughout the whole orbit. Okay? You don't have to do that. You can just put R0 here, but this is a nice thing. Remember, these parameters, this gamma and the R, are dimensionless. the lattice radius, its dimension, meters. Epsilon, dimensionless. Okay, so you got a dimensionless, and then Cartesian, A and B, they're both meters, both dimensional in meters. Okay, so that's the other thing to extol the virtues of R and gamma is they're dimensionless. They don't give a damn about what unit you're using. So use whatever you want, and I like that. R0 equal 1. Okay, I should put a 0 on that. All right, so this guy right here. I could square, take take the square root of that. This, we do have a plus or minus here. We can have either this or write that. This will give us a formula for the semi-major radius of whatever. Hyperbolas and ellipses have that. It will be r over r plus 1 sine gamma. Lattice radius is similarly related. B squared over A turns out to be 2r sine squared of gamma. Okay, so for each of these conic sections, we have nice formulas. Okay, now I'm going to go through these constructions fairly quickly that I'm showing you here. Here's a construction with a -3/8 ratio. Ellipse, obviously. We're in the elliptical region for the focal point. Okay, and I just want you to see that Euclid would be happy with what we're doing. The idea is that I can build the orbits exactly with a ruler and compass, so far as the mathematics of physics of Coulomb field is exact. That is what we're doing here. So basically, this is the first step when you have got your two focal points on some arrangement like that. So you now have the unprimed radius of the P that you set, and that's 1, a unit in our units. Then you have another one that's longer or shorter, that's the prime radius, the distance to this point where there isn't anything, the vacuum point, you might call prime focus. Okay? Well, the first thing you do is swing an arc up to here to find, basically what you're doing, see, is you're finding the 2A. You need that 2A. Okay, that's the thing that goes in the denominator to give you total energy, right? So K over 2A is total energy. So we need the 2A for a number of things. Mainly what we have to do is we have to take this 2A and bisect it. Once we know what A is and find the center between these things, we're good to go, because I'll know where the aphelion of the orbit is, and on this side I'll know where the perihelion of the orbit is, and then it's very easy to get the semi-major B, which will be roughly about there. That's the nitty-gritty of this geometrical construction that I'm going to show you. And as I say, I'm going to go through these fairly quickly, but I've carefully written down the instructions so you can study these slides afterwards and get the exactly what we're doing. Here's the way I do it. I strike a radius R arc. That's this guy here. I go and let's see if I can remember what it was. The radius R is, let's see if I got the point P prime. We found this point right here. So I strike an arc, and I've got to figure out what it was. I think that arc came. Embarrassed now because I can't remember exactly how I set that arc. About the focus, let's see. Oh, okay. I obtained the radius A first here. Now that's a fairly.
Bisect.
Let's see if I can.
It's the image of your bisection. You're bisecting the
That's right, that's
line
right.
segment.
That's right. Thank you. You're way ahead of me on this one. Yes, that's the thing we have to do. This is 2A. I have to bisect that. And once I've done that, I can draw, something that actually has radius A around the main focus. Okay, and it's tangent to a bisection line, which is what we did right there. Okay, so this is a bisection problem. Yeah. Okay, once we've got that, now I've got something that's perpendicular to the radius that I can work with. And the next step on this is to draw a radius A circle around this guy. Okay, so that radius A circle can be matched up with a radius A circle around the main focus. So we got the prime focus and the thing, and we're making a symmetrical object. And once I've done that, where they go, they bisect this thing, which is the A epsilon distance right here, and that's the center now of the orbit. Now I've got a Cartesian description of this orbit, an AB description, okay? And there's B right there, plus and minus, okay? So at this point we can do remember our construction where we drew a circle of radius B and a circle of radius A and just filled it up with an ellipse. I think that's basically what we do. So there's a circle of radius B, okay, and then there's a circle that's of radius A, and of course we also have a circle of the, let's see if that's right, yeah, there's the epsilon, but this is the A epsilon right here. So that gives us an orbit, and these are actual numbers for this orbit. Okay, and you make sure that it really is tangent to that and stays inside the region where it should be. Okay? All right. Now the hyperbola is a little trickier, but here's the main thing that we're using. The major diameter 2A is the difference between the two radii that we're going to be playing with. So I'm going to have a focus point here and here now with this particular choice of 0.5. So now we're in the repulsive hyperbola region. So that's what we're going to be building from this point, given this momentum. Same momentum we had last time. Okay, same R scale that we had last time. Major radius is half the difference. Okay, the R prime. So that's what we got to build. Major diameter 2A needs to be centered. That's the thing that's right now. I can just swing this up here and get an R prime plus R, but I need R prime minus R, so I really need to swing that around the other way. And once I've done that, then I can get R over 2 by doing a bisection right there. And then, that's what this says, bisect, then bisect this to get focal axis F prime. This right here is, now I've got a perpendicular to the axis of our conic section. And of course, that has got to be the axis. Epsilon is pointing at the focus, but you see this is the focal locus. So there's no focus that would be had up here. This is the focal focus locus right here. So that's where the new focal point was in this weird regime of repulsive orbits. And bisect that guy one more time. I think that gives me enough that I can build using these focal points and the center. I can go ahead and start building a orbit. Copy the circle, the major radius R prime minus R prime over 2 about the orbit center. Remember, that's once I get that radius, I got to move it over. But that's pretty easy with a ruler and compass. Then I got the focal circle, okay, and that gives me the B right there. So now we've got the A and the B, and notice B is a little bit bigger than A, so this is definitely a hyperbola. And you go ahead and build the box. Now you've got the rectilinear components, but they're tipped, obviously, because the eccentricity is tipped for the hyperbola. So you're going to see a hyperbola that's coming up here, and here are the asymptotes too. The diagonals of that box. Remember when we do these boxes in different orientations, okay, with impact parameters and things like that. Right now we're not using the box that shows the impact parameter perpendicular to any line of motion, but we don't need that at the moment. So next step is to actually draw a section of hyperbola. Or there's the R arc right here. It doesn't show up very well. That arc right there. Just do an arc between the asymptotes like we did for Rutherford, except now it's out in the middle of nowhere. And our arc minus 2A distance, we mark that off, okay, and then use that to draw the the intersection that gives the thing. This is construction based on the difference. Draw an R arc, set your compass to R minus 2A, and then draw that arc about the focus F prime. Okay. Once you do that, there'll be an intersection right there. There's the arc around this focus connected to the arc around that focus. So there's a point on the hyperbola. It's pretty close to the asymptote, isn't it? And of course there's another one down here. You complete the arcs and you get 2 points for the price of 1. Okay? Then